Computer. Okay, welcome to Lecture 7. Any questions before we get started? Let's get started. Let's see, share screen. Share. Okay. Good. Any questions during the lecture? Of course, just as always, type it in the chat. Today, we're going to be talking about special and general relativity. We're going to do it in a single 60-minute lecture. And so it's going to be very, very surface. There's not a lot we can touch because, people get their PhDs in special and general relativity. Question from Joseph: what is the best way to prepare for the exam? So we'll go over that. So what I'm going to show you in the next few slides are the topics that you're going to be responsible for. So I would say the best way to study for the exam, that almost all the questions except two are straight from the textbook. So what I would do if I were you is read the textbook very carefully, concentrate on these issues. So I went over the exam. It's got 66, 67 questions on it in Moodle, and just wrote down the topics that I cover in the questions. Here are the topics. And of course, I would go over the homework too, because again, the homework also comes from the textbook. So chapter 1, chapter 2, chapter 3, chapter 4, and chapter 5. And this is posted already on the exam guide in WebAssign. So all the files you need are going to be posted under resources on WebAssign. Is the exam open note? I have no way of monitoring what you're doing. So can you go back to chapter 1? Sure. Now, again, this file is posted down. I think it's exam guide 1 under resources on WebAssign. So I wouldn't bother writing down what you're seeing right now. Just go to WebAssign resources. Also in WebAssign resources are all of the PowerPoints from the publisher and my slides. If you only had time to do one set, I'd probably go with the publisher PowerPoints, again, because those PowerPoints are directly from the textbook. Whereas mine, I cover material, other material too, that I think is important. Notice solar system distances of plants. That's supposed to be planets, okay? Chapter 3, chapter 4, and chapter 5. So there's a lot of stuff on chapter 5. So again, just based on the size of the notes, you should spend a lot of time on chapter 5. So textbook, homework, the PowerPoints, and then my PowerPoints, and then if you have time, you can review the lectures, although that takes some time. And again, those are under YouTube, and you can find the location on the syllabus. Here are the equations you're responsible for from the equation sheet. And again, the equation sheet formula file is also posted under resources on WebAssign. Note that, again, you are not responsible for calculating anything. You are responsible for things like, if I double the radius, double the distance between two objects, how does the force go? Does the force go up? Does the force go down? Does it go down by half? Does it go down by a quarter? You'll be very responsible for that. If I double my mass, and everything else stays the same, how does the force change? Or the orbital velocity. If you double the radius of the orbital velocity, how does the orbital velocity vary? And that would be the 1 over the square root of 2, for example. So it's those sort of proportionalities you're responsible for. But again, there's no calculation per se. You won't need a calculator for the exam. And you are responsible for 2 dead white guys, 3 laws, okay? And unfortunately, you're responsible for those by number. What is Kepler's second law, for example? A question similar to that is on the exam. Okay. And you're responsible for the 5 dead white guys that we talk about in this course. Copernicus, what he's famous for, Galileo, Brahe, Kepler, the contemporaries, what they're responsible, what they're famous for, and then Newton, the greatest, one of the greatest human beings, well, at least in terms of his intellect, although not necessarily his personality, that our species has ever produced. Okay, any questions about the exam before we go on? So let's get started. So we're talking about, we're going to talk about three topics. Three topics are what we call classical relativity, special relativity, and general relativity. Classical relativity is our day-to-day lives in terms of how things are relative, and we'll talk about that in a second. Special relativity and general relativity are two of the greatest theories, again, ever invented by mankind. They're both invented by the same person, Albert Einstein, the second greatest human that our species has produced. You will be responsible for the difference between these two, and we'll go over this in some detail. How long do you have to take the exam? You have 75 minutes. I'll open the exam Tuesday at 8 a.m. It closes at midnight, so you can take the exam anytime during that day. Once you start the exam, you have 75 minutes to finish. And it's not 75 minutes, you can't take a break, okay? It's 75 minutes literally from the time you press start until you finish. So it doesn't, there's no cumulative timing. You have to finish it in 75 minutes, and if you don't, it will automatically submit whatever you have at 75 minutes for you. Do we have more than one attempt on it's an exam? And no, you don't, sorry. Will we not have exam class on Tuesday? That's correct. There is no class on Tuesday. And we do not meet on Tuesday at all. So it's similar to like if we were in class, okay? So let's go on. So let's start with classical relativity. Classical relativity is the fact that we know intuitively that motion is relative. So we're in an airplane that's moving at, well, in this case, 1,670 kilometers an hour, which is really fast. Well, that's over 1,000 miles an hour. But inside the airplane, it appears that things are moving still. And so every day, I mean, we're driving in a car and it seems like we're still inside the car, even though the outside is moving. And, you know, the earth is spinning around at 1,600 kilometers an hour. The earth is rotating around the sun at, you know, dozens of kilometers a second. And the sun, the solar system is moving around the galaxy at hundreds of kilometers a second, and the galaxy is moving through the universe at thousands of kilometers a second. So we've got all these motions, and the fact that motion is relative is just common sense. So here's a question. You're under a windowless airplane. The ride is smooth. Is it possible to figure out that you are moving? Let's see. Well, will it be during class time, or do you have all day to do it? Going back to the exam, sorry. The exam opens at 8 a.m. on Moodle. It closes at midnight. So you can take it anytime. You can take it during our class time because you obviously have that time free, or you can take it any other time. But if you have not finished by 11:59 p.m., it will automatically submit for you at 11:59. So don't wait until the last second. Will there be multiple question times, or they're all standard multiple choice? So the exam will consist of true, false, multiple choice, fill in the blank, and ranking. Okay, so all four of those types. It won't be any sort of essay or calculations, but it will be true, false, multiple choice, fill in the blank, and a ranking. Okay. You're under windowless airplane. The ride is smooth. Is it possible to figure out whether you are moving? Answer A, yes. Drop an object and see if it falls vertically or is deflected backward. Think about all the times you are on an airplane or even on a car. Yes. Shine a light forward up the aisle and backward down the aisle and measure the difference in their speeds. Yes. Throw a ball forward down the aisle and throw a second ball backward down the aisle, then determine which one went further. Or no, there's no experiment inside the plane that can determine whether the plane is moving at a constant speed or is stationary. Let's bring up the poll. Yes, so the question is, assuming that you're cruising in midair, not landing or taking off, the air is crystal smooth. So, I mean, it's a thought experiment. In a real experiment, you would feel the vibration. Although I suppose what you could do to simulate that is you have the plane on the ground and you have, you shake the plane and you'd have noise speakers on the outside. So 5, 4, 3, 2, 1. So that's correct. There's no way to tell whether you're moving at a constant speed or you're not moving at all. A corollary to that is the fact that the speeds that you measure inside the plane and the speeds that are measured by somebody outside the plane are going to be different. In other words, you throw that ball towards you on the plane and you say it's moving at 10 meters per second, whereas someone that's measuring the speed of that ball outside the plane is going to say that ball is moving at 1700 kilometers meters per second. So it's the corollary to this common sense, what we call classical relativity, is there's no way to tell whether you're moving or stationary, but it does mean that the speed of an object depends on your reference frame. Okay, the speed of the ball you throw depends on whether you're on the airplane or off the airplane. That's common sense. And so in classical relativity, motion is relative. The laws of physics are the same for all unaccelerated observers, no matter what their motion. So you have two spaceships passing, and neither one can say which is stationary and which is moving because the motion is relative. So that's classical relativity. That's what we were born and raised with. Then you have Einstein, who started with special relativity. And the reason why I went so slowly over this thought experiment, I'm sorry, Joe, most people did get a poll. We'll try that again in a minute. Okay, so special relativity. The reason why I went over that so ponderously is because in special relativity, things are not relative. Things are absolute. And so the fact that they call it relativity is kind of weird. So in special relativity, the speed of light is constant, independent of the observer. This makes no common sense. It would be like you've got a ball that you throw on the airplane and you measure its speed, and I measure the speed of that ball from the outside as the plane is moving by me, and I measure exactly the same speed of the ball. That makes no sense, and it just violates common sense. And so what Einstein said is the speed of light, not of the ball, but of the light itself, depends on the motion, is constant, independent of motion. So if a light is switched on, how fast will it appear to go from the perspective of someone inside the rocket? Remember, electromagnetic radiation, light always moves at the speed of light, which is designated as c. So let's go to the next poll. And there's actually two polls back to back here. Poll number one is if it's how fast will the light appear to go from someone inside the rocket if I'm moving at half the speed of light. So if I'm moving half the speed of light and I'm shining a light beam that's pointed in the pointed direction, how fast would the light appear to move if I'm inside the spaceship, and how fast would the light appear to move if I'm outside the spaceship? And remember, classical relativity is the velocities add. So here are the two questions. Is there anyone specifically who can attribute classical relativity to? Well, a lot of that's just common sense that motions add. So I would say, it's just ancient. I think the person who put mathematical teeth in that would be Isaac Newton. So we're not speaking of Lorentz transformations in this class. I will actually show you the equations, but you're obviously not going to be responsible for them. If you know Lorentz transformations, are you a physics major? Yeah. Yeah, you should be in the astrophysics course. In fact, I would strongly recommend you take that course after you finish this one. It's a great course. Okay. Okay. Oh, thank you. Yeah, I try to make it entertaining. Okay. So 5, 4, 3, 2, 1. Okay. So most of you said that if the light switched on, it will appear to go the speed of light inside the spaceship, and that's common sense. The number 2, most of you said that it would also appear to go the speed of light from outside the spaceship, which makes no sense. So here we go. Inside the spaceship, it looks like it's the speed of light inside, but it's also 1.0 c outside. And again, if you think about it, and if you think about it in terms of balls, this can't be. So what special relativity says, and this violates common sense, I'll give you the 3 postulates, and then we'll show a little video that hopefully will put some meat on them bones. That the speed of light is the maximum speed in the universe, and it's always the same relative to observers. So here we've got a bullet that's being shot at 1,000 kilometers an hour from a car that's moving at 100 kilometers an hour, and the observer sees 1,100 kilometers an hour because it's the car plus the bullet. Here we've got a spaceship moving at 0.1 c, shooting a light beam, and so the light beam to the outside observer should appear to be moving at 1.1 times c, but in fact he sees c. So common sense, which we observe day to day, and the way the universe is really made are different. There is no absolute frame of reference and no absolute state of rest. Okay, so that's just copied over from classical relativity. So Alex, I'd love to teach 328. I have not yet taught it. So Steve Reynolds is the person who usually teaches it. He's a great teacher. I'm not sure who's scheduled to teach it next time. And here's the third one we haven't talked about, but velocity is a measure of distance over time. And so if the velocity is the same for 2 people, that means that distances and times have to be different for different observers. And that makes no sense. Will we discuss redshift as it relates to Doppler effect? Yes. Not for this exam, but yes. So the answer for both questions was 1.0 c. Absolutely. That's the paradox. That's the thing that makes no logical sense. So the ramifications of these special relativity postulates, if the postulates are true, space and time cannot be true if space and time are absolute and fixed. In other words, if the velocity is fixed, space and time vary. Okay. So in fact, time depends on your relative motion. So the time I measure and the time that it appears that you are measuring, that you are on the spaceship are different. So when I see a spaceship flying by, the time that it appears to me when I'm observing the spaceship is slower. In other words, as I watch you stream by, it appears that you are living at a slower speed than I am. And you, when you look at me, it appears as if I am moving slower. I have a slower clock than you do. Okay. And when you get closer to the speed of c, it's a dramatic difference. And also distances are different depending on the relative speed. And again, so my appearance of speed to you and your appearance of speed to me are completely different. And it's almost like there's no objective reality here, which is unfortunately true. So making sense of relativity, one way to think of it is that when we're kids, are the mini quizzes part of the completion grade? No, the polls are not graded. We have this concept of up and down, and it is up as you look up, down as you look down, and that makes sense. Only later do we realize that up and down are actually very different, that the people in Australia, for example, their up and down is very different than our up and down. In fact, they're in completely different directions. We know that intellectually, day to day, it doesn't affect us, but it's like we have redefined up and down in a very different way as we grow up. So what is relative? Why is it called special relativity?
Relativity, the idea that everything is relative, right? Relative to your perspective, your upbringing, your age, your place, and orientation in space and time. Except that plenty of things, in fact, perhaps most things, aren't relative. For example, George Washington was the first president of the United States. World War I happened before the movie Star Wars was made, this picture shows 3 apples, and so on. It is true that certain things are relative to one's perspective. Is the apple on your left or my right? Is 50 degrees Fahrenheit hot or cold? Is a car fast or slow? Big or small? And the fact that they're relative is precisely what makes these concepts less interesting to scientists. In physics and in most science, anything that changes if you change perspective can't be a fundamental property of the universe. Only things that are absolute are considered physical or real. And for a long time, physicists thought that distances in space and intervals of time were absolute fundamental properties in the universe. The special theory of relativity, first described by Albert Einstein, was merely a statement of the realization that we were wrong. Distances in space and time are actually relative. They change depending on how fast you're moving. But more importantly, Einstein also described several quantities related to space and time, which are absolute. The distance between 2 events in space-time, the energy momentum of an object, and of course, the speed of light.
So in this, he talked about the difference in space-time. So special relativity is all about space-time, that space varies depending on how fast you're moving. Time varies depending on how fast you're moving. But space-time, which is, we're not going to get into the calculations, but space-time, which is a measure that takes into account space and time, that doesn't vary. Okay, here's another video.
Speaking of the moon, you probably also learned that if a sheep is moving 2 miles per hour relative to a train, and that train is moving 2 miles per hour in the same direction relative to the ground, then the sheep is moving 4 miles per hour relative to the ground. 2 miles per hour plus 2 miles per hour equals 4 miles per hour, right? False. Experiments in special relativity have confirmed that velocities don't simply add together, and so the sheep will in fact be moving very, very ever so slightly slower than 4 miles per hour relative to the ground. And the formula that correctly predicts this deviation from just adding the velocities is v1 plus v2 divided by 1 plus v1 times v2 over c squared. It's not a very big effect, but then again the Earth looks pretty flat, doesn't it? But the Earth isn't flat. If I walk 10,000 kilometers away from my cat, and you continue on walking 10,000 kilometers more, you're not 20,000 kilometers away from my cat. You're just 12,750 kilometers away. In fact, the farthest on Earth you can get from anything on Earth is 12,750 kilometers. It's the earthly distance limit, though we normally call it the diameter of the Earth. And similarly, when you try to add 2 velocities together, there's a cosmic speed limit of 300 million meters per second. That is the speed of light. So just because to our eyes the Earth looks flat, velocities look like they simply add together, and light looks like it doesn't attract gravitationally, is that an excuse to mislead ourselves and our children about the true nature of things?
So, so Matthew, if you're running towards someone at the speed of 1c, would I view his speed as 1c? You would view his speed as 1c. There is no scenario anywhere in the universe where any speeds in any way that you add it ever exceed 1c. Abby says, is space-time orientable? I'm not sure I understand the question. Could you rephrase? Would V3 equal, so Alex, yeah, this doesn't matter whether the Earth is flat or round. Our universe is built around special relativity, and if special relativity didn't hold, we would be in a very, very different universe. Who made these videos? So the videos, a lot of the videos I show, not all of them, are from what's called Minute Physics on YouTube. I would strongly recommend you see that. And luckily they don't send nasty copyright takedown notices when I post my lectures. Okay, lots of other people do. Okay, so that's special relativity. Special relativity says that the speed of light is absolute and space and time vary. That's what's important for you to know. Okay, so now we're going to talk about general relativity. Special relativity was about velocities. General relativity is about gravity and accelerations. How are space and time relative? So the space shrinks and time lengthens as your observed velocity changes, okay? The equations for those, as someone mentioned earlier, the Lorentz equations, there's equations for those changes, but you're not responsible for those equations. But just for the purposes of this course, space and time vary. The time that I have on my spaceship is different than somebody else observes. So for example, if I travel very, very fast on my spaceship and it goes to Alpha Centauri, and then it comes back and it takes 20 years, 10 years out and 10 years back, I will come back and I will have aged 10 years. I'm sorry, I would have aged 5 years, whereas on the Earth, 20 years has elapsed. So there's a real effect of different time on different objects. And we'll get into that in terms of GPS in just a minute. So here we've got, this is from the movie 2001, which was made in the 1960s. It's the greatest film ever made in the history of cinema. Not that I have an opinion about that. And what this is you have an astronaut that is running in a rotating spaceship. And so it feels like he has gravity, but in fact, it's just a Ferris wheel that's rotating around, okay? Let's see, Sam, when you, some of your motion, it's not a bad analogy. Okay, so general relativity is the statement that you cannot tell the difference between acceleration and gravity. And so that's just like what you saw with the this motion here, okay? That he is actually being accelerated by this rotating Ferris wheel. There's no gravity in the spaceship, but it feels like there's gravity. And what Einstein said is, it feels like gravity because it is gravity. So gravity and acceleration are one and the same thing, according to Einstein. You can't tell the difference between acceleration from gravity or motion.
The 28-year-old Albert Einstein is still a patent office bureaucrat. It has been 2 years since he published his special theory of relativity. In 1907, Einstein agrees to write a new article explaining special relativity.
It's called special relativity for a reason, and that was because it really only dealt with moving at constant speeds.
Einstein realized that his theory failed for accelerations. But in our universe, everything accelerates.
Einstein knows that for his theory to work, it has to account for everything in the universe. And the ambitious Einstein decides to advance an even more radical interpretation of the universe, a general theory of relativity. Doing this will require him to take on his scientific hero, Sir Isaac Newton.
Newton said that if an object falls, it's because there's a mysterious force called gravity pulling it down. But you know, Isaac Newton himself was not satisfied by that. Objects move because they're pushed, not pulled. So what is pushing this? Newton didn't know. So Newton simply threw his hands up and said, I don't know. So I'm going to invent something called gravitational pull. And Einstein said, no, this theory can't be right.
He's in his office at the patent office, looking out at the window, and he imagined a man working on a roof. And he begins to wonder what would happen if one of those men were to fall off the roof. He had a vision. The man will not actually be feeling his own weight.
He would be weightless. And then he imagined, if you're in an elevator and somebody cuts the cord, what happens to you? You fall. But the elevator falls at the same rate you do, so you are weightless inside the elevator. So then Einstein got it. There is no such thing as gravitational pull. The Earth has curved the space around me, and space is pushing me into this chair. Space itself can be curved. Why does the Earth go around the sun? Most people would say, well, the sun's gravity is yanking the Earth toward the sun in a circle. Wrong. The Earth is going around the sun because the sun has warped the space around the Earth, and space is pushing the Earth toward the sun. He had a new theory of gravity, a new theory of the universe.
General theory of relativity is one of the greatest achievements of the human mind. It is beautiful and simple and profound. And all the best theories of the universe are just that.
So general relativity is hard to understand. I'm going to show you actually a series of videos about it to try and explain it. And you saw a video of a kind of a sheet, and you're pulled towards a sheet, and that makes sense because that's a common sense analogy. The problem is that in Einstein's theory of general relativity, gravity is a warping of space-time in all dimensions, which we can't visualize. And it's that warping that causes the acceleration. So it's the shape of the universe, of the fabric of the universe, that causes gravitational acceleration. And that, again, makes no logical sense. So the postulates of general relativity is gravity is a deformation of space-time. Space-time is another word for just the fabric of the universe. And this is a two-dimensional analogy of the three-dimensional universe, that a massive object will cause a warp in the fabric of the universe, which we call space-time. And so the closer you are, that the more that the space-time, this fabric of the universe, is warped, the stronger the pull. And it feels like a pull because remember, acceleration is change in velocity or change in direction. And as this ball comes towards this warping of space-time, it's going to move faster and it's going to change direction faster. And so it'll feel what we call a stronger gravitation.
To look at the body's influence on the space they're embedded in. And so in Einstein's picture, a massive body makes a depression in the space-time around it, so that other bodies following their natural paths tend to be attracted to this depression.
And here is the analogy.
And so you put matter and it warps space-time. And so if I have another object, it also warps space-time. They feel that and they're attracted to each other. And so that's Einstein's picture of gravity. Objects warp space-time, feel that curvature, and move accordingly. If you have more mass, it's going to bend space-time more. And so if you have objects here, they are going to respond to that, right? And so you put something there, now it's attracted. Now, in reality, that big mass would feel the warping of space-time by the marble too, right? It would move a little bit, but we usually ignore that. You know, the Earth makes the sun move a little bit, but it's so small you can ignore it. The moon makes the Earth kind of wobble around a point 3/4 of the way from the center of the Earth. We usually don't account for that when we're looking at satellite motion. Well, instead of just letting go of one, what if I give it a sideways push? Now it orbits. Now it's losing energy, which wouldn't happen in the solar system, right? Not noticeably. There's some perturbations from other planets and things, but this one does lose energy and spirals in. Why is everything going in the same direction? Well, the answer is it wasn't. Different directions. But there was a preferred direction. The disk it formed from had a slight preference one way versus another, and things going the opposite way got eliminated, and when it's all said and done, everything's going the same way.
Yeah, so Matthew, so space is warped when big mass existed, in which way does it bend? Here's the problem. What you're seeing are analogies, but analogy isn't truth. Analogy is just making it easier to think about it, because in reality, it's a three-dimensional, it's a three-dimensional warping, which we cannot easily visualize. And so there's no direction to it. It all gets warped, and the more it's warped, it's more warped the closer you are to a massive object. If space tells matter how to move and matter tells space how to curve, does that mean that space is the dominant force because space is controlling matter's movement? It's a dance. Space and matter are dancing relative to each other. So Hannah, are you also a physicist? Because that phrase is directly from a very famous general relativity textbook. So another video. Well, I'm sorry, no. So here's a compare and contrast to Newton. Newton said that there's a gravitational force, a pull. So Hannah, it's impressive that you knew that quote. That gravitational force acts instantaneously, and it's a mysterious force. There's no rhyme or reason behind it. And the equation for the gravitational force is gm over r squared. This is the equation we're going to use in this course, because for all intents and purposes, it works great in our solar system. It only fails in extreme circumstances, say around black holes and neutron stars. Einstein said that gravity and acceleration are one and the same, and gravity is a deformation of the structure of the universe, which we call space-time. And we haven't talked about that, but as it warps space, it also warps time. And if you think that's hard to think about, that's why, we spend years studying general relativity, and why until recently, when general relativity became really a hot subject, it was kind of a sidewater because it was so mathematically and conceptually difficult. And his equation for gravity is this relatively simple equation, GUV equals 8 pi TUV, but that is a simple equation that expands to one of the most complex mathematical equations in all of science. And that's why it's very, very difficult to study. But he is saying what this equation says is, as Hannah so promptly said, that the T is a tensor, and that is the deformation of space-time, and the G is the mass. Okay, so the tensor tells the mass how to move, and the mass tells the tensor how to warp. Okay, another video.
In 1907, just a couple of years after he does his theory of special relativity, Einstein's a little bit worried. Special relativity only applies to bodies in a constant state of motion. He's trying to figure out, how does that deal with acceleration? There's another problem that we had all inherited by then from Newton, which is that there's something called gravitational mass, how much something weighs in the gravitational field, and there's something called inertial mass, which is how much force does it take to push it and get it moving. And inertial mass and gravitational mass are the same, but they're two different ways of explaining them. And Einstein really hated when there was two theories explaining one phenomenon. He wanted to unify it. And so then he has what's called his happiest thought. He imagines a person just falling, free-falling in space. And he says, well, that person wouldn't feel gravity as he accelerated downward. And likewise, he imagined somebody in an enclosed elevator who's being accelerated upward in outer space where there's no gravitational field. He said, well, that person would still feel like there's gravity. If he took something out of his pocket and dropped it, it would fall to the floor at an accelerated rate. There'd be pressure up on his feet, just as if he were standing in a stationary elevator car on the surface of the Earth. So he realizes what he calls the principle of equivalence, that the effects of gravity and the effects of acceleration are equivalent. So there must just be one explanation for gravity and acceleration. And that's what the general theory of relativity is. It takes a notion of constant velocity motion, which is special relativity, and says, how are we going to apply it to accelerated motion? And he really comes up with this notion of a fabric of space and time, as if it's a fabric that sort of curves like trampoline fabric. You roll a bowling ball on it and it curves because the bowling ball's there. Then if you put some billiard balls going afterwards, they kind of move towards the bowling ball. Why? Not because the bowling ball has a particular attraction, but because it's curved, the fabric on which they're rolling. Now imagine that in the 3 dimensions of curving all 3 dimensions of space. Pretty hard, right? But also imagine it in 4 dimensions, because what gravity does, it's a curving of the 3 dimensions of space plus time, the curving of space-time. Pretty difficult, but it all amounts to the most elegant theory in the history of science, the general theory of relativity.
Yeah, so you know, in this very brief introduction, you're left with more questions than answers because we can't go into great detail. But the time varies depending on your acceleration. Time varies depending on your velocity. So there's in special relativity, your time varies depending on your relative motion. And in general relativity, your time varies depending on where you are in a gravitational field. And so this thing that we thought was constant, that the time I measure on my watch is the same as the time that you measure on your watch, is absolutely not true for 2 effects. And that doesn't jive with our common sense day-to-day life. And it doesn't make any sense. And this is why it's taken so long to really validate that. But the thing is, this is the way our universe is made. Our universe follows these laws exactly. Every time people tried to validate special and general relativity, it is completely validated. This is our universe. So Joseph says, I don't understand how time varies. Yeah, if you knew how time varied, you would be better than any human on this planet. Nobody knows why time varies. It just does. We follow these laws, these equations of general and special relativity. We don't know why that is. That's just the way our universe is built. So gravity is an analogy for the bending of space-time. Yes, that's correct. Is this why people on the ISS age slower than people on Earth? So there's 2 effects. And in fact, I've got a video to explain those 2 effects in the concept of GPS, but it's the same concept as on the ISS. So the people on the ISS age slower because of 2 effects. One effect is they're moving much faster than us. They're moving at 17,500 miles an hour, but also they're in a gravitational field that isn't as deep as ours. So they're a little farther away, which means that they will age slower because of their faster velocity, but they'll age faster because they're farther out of the gravitational field. And those 2 effects don't quite balance. Which postulate does E equals mc squared fall under? So E equals mc squared is a postulate from special relativity. We don't cover that because I didn't want to get too far afield. Okay. Another short video.
Similarly, the general theory of relativity was essentially the recognition that in fact neither the acceleration nor the gravitational field experienced by an object are absolute quantities. Accelerations can transform into gravitational fields, and vice versa, depending on your perspective and the path you take through spacetime. The more fundamental absolute quantity is the curvature of spacetime, which you can think of as a kind of underlying or absolute gravity. Special and general relativity are, at their core, not about what's relative. They're about what's real, irrespective of perspective. If everything were relative, then there could be no science, no laws, no justice, just opinion. Science exists because it turns out there are absolutes in the universe, truths which are the same regardless of your perspective. You might even say that science is simply about finding the truths that will still be true if you remove the scientist. So, goodbye.
This is actually one of the things that's most upsetting about the last few years in our country is that people have degraded the concept of an objective truth, an objective reality. There is an objective truth out there. All statements are not all political statements. And turning a science agency such as the CDC into a political agency is just, well, anyway, that's not what this course is about. Alex, if time is bent by the presence of a physical object, then doesn't that mean that time is somehow linked to and then affected by the physical world? Absolutely. That's exactly what both general and special relativity say. That time is a function of the physical world.
Imagine learning for the first 18 years of your life that the Earth is flat. All through elementary school and high school, you grow up hearing about the flat Earth we live on and doing boring flat Earth physics homework, and then, if you're lucky enough, you get to college and, psych! For the first time they show you a globe and say, sorry for lying, the Earth is actually round. Well, this is, unfortunately, exactly what we do with... You probably learned that objects attract each other based on their mass, so you probably grew up thinking that light can't possibly be affected by gravity because light is massless. I know I did. Well, guess what? The source of gravity is not mass. It's energy and momentum, which light certainly has. Of course, regular matter does too. So not only does light get bent passing by a star or planet or black hole, but light attracts the planet or star or black hole in return. To be sure, it's only a very, very small amount, but a small amount is not zero. Anyway, the point is that Newton's law of gravitation is just an approximation. Good enough to get us to the moon, but not perfect. General relativity...
I don't know why that cut off. Anyway, let's go on. So let's see. What does it mean to bend time from Alex? So in the video, they said bend time. What they actually mean is just change time. Time is just a single number. What example were you talking about before when you travel to a planet on a spaceship where you age only 5 years while 10 years elapses on Earth? This is called the twin paradox. So Google that when we have time. That was just an example that the time varies depending on your velocity and your acceleration. So essentially, time is not real. No, time is very real. It's just not absolute. And gravity is very real, but gravity is a result of the warping of space, of the fabric of space. So in Robert Forward's book, Dragon's Egg, the inhabitants of a neutron star see an approaching rocket stand still in space. No, in fact, it's a perfect illustration of space, of the gravitational time dilation, because the people that lived on the surface of that neutron star are in a very, very strong gravitational field. And so their time goes much faster than people on the outside. So they see things on the outside move at a much slower rate. By the way, that's a great book, that and the follow-on book to that. And Robert Forward is a physicist, and so all the physics with a single exception are correct. And he knew that one exception was, and if you're interested, I'll tell you about that. So relativity in a nutshell: the special theory of relativity, the laws of physics are the same in any reference frame. The speed of light is the same for all observers, and time and space vary. And we call that space-time, okay? So three dimensions for space and 1 dimension for time. The general theory is that gravity equals acceleration. Gravity is the distortion of space-time by mass, and it predicts the bending of light by gravity. And it also predicts gravitational waves, which is the warping of that space-time, which we first discovered in 2015. We'll be covering in this class. So this is pretty much a summary of what you need to know about general and special relativity in the context of this course. And note, space-time is relative to special theory of relativity, that time and space vary, and gravity equals acceleration, and gravity is the distortion of space-time, is a concept of general theory of relativity. How do we know that gravity and acceleration exist and it's not just acceleration? Well, they're just two terms for the same concept. You don't actually age any different from your own perspective. Yeah, that's correct. Okay, so here's someone asked a question about the ISS and why they age slower on the ISS. Here's the answer to that question.
We take navigation for granted these days. GPS receivers guide airplanes, cars, and even cell phones. But did you know that the Global Positioning System is basically a big clock in space? There are 30 GPS satellites in orbit, and they just broadcast where they are and what time it is. All your phone GPS has to do is receive signals from 4 satellites, and it can triangulate its location in the 4 dimensions in which we live: 3 space and 1 time. But actually, it's not that simple. In order for navigation to work, the satellites carry atomic clocks accurate to the nanosecond. Otherwise, your GPS receiver might tell you you're halfway across town when you're still in the driveway. And special relativity tells us that moving clocks run slow, while general relativity tells us that clocks run faster higher in a gravitational field. These effects don't quite cancel. General relativity wins out, and time indeed runs faster up in orbit with the satellites. But some of the engineers working on the first GPS satellite couldn't bring themselves to believe that their clock would actually run fast just from being higher up, so they sent it up uncorrected. Within minutes, it was off by enough to impair GPS navigation, and by the end of the day, GPS receivers would have been wrong by tens of kilometers. Needless to say, the engineers turned the correction back on, and these days, they trust general relativity. Oh, and one last thing. GPS is also a nuclear weapons detector. There are always at least 4 GPS satellites visible from any point on Earth, and because of this, any nuclear detonation will be seen by enough satellites to pinpoint exactly where and when it took place.
Anyway, so I've got a bunch of questions here, and then we'll just open it up for QA. So first question, let's see, that was, what explanation does general relativity provide for gravity? Yeah, so Hannah, that interstellar is, everything you see in there is correct, except of course the ending. And yes, the difference in aging, especially when they're on the water planet, that's all correct. That's actually what would happen. You would age faster on the lower gravitational well relative to the outside. Okay, 5, 4, 3, 2, 1. Yeah, so here's the thing. This is one of the examples where you really have to read the question carefully. So gravity is directly proportional to mass is true. Gravity is the weakest of the 4 uniform forces is also true, but they were not the explanation that general relativity provided. And so if you read the question carefully, the only correct result is gravity as a result of curved spacetime. Okay, and gravity is inversely proportional to radius. Actually not true, because it's inversely proportional to the distance squared and not necessarily the radius. Okay, so does that mean that you would age differently on Mars or other planets of the solar system? Yes, that is true, but the difference would be minuscule. It would be in microseconds, so you wouldn't really tell the difference. When those GPS satellites are sent into space, were they purposely distanced to be able to triangulate for a nuclear blast? So yes and no. So GPS satellites are not in a high in geosync orbit, and they're not in a low Earth orbit. They're in an intermediate orbit, which means the relative positions of the GPS satellites relative to each other is constantly changing. And certainly the orbits needed to be designed such that you could see at least 4 of those satellites from any place in the globe at any one time, because you need 4 satellites to figure out your GPS direction. And for those of you that have old-fashioned GPS receivers where you can actually see the GPS satellites in orbit, you usually can see about 8 or so. But that means that because of those orbits, you could also easily see any point on the Earth, and so it just made sense that they would put nuclear explosion detectors on those satellites, because they're always observing all of the Earth. Hypothetically speaking, could some astrophysics savant manipulate space-time to achieve immortality? Well, again, it's the way that other people observe your time. So certainly if you had a very fast spaceship, you could travel forward hundreds of thousands of years into Earth's future, and your time only advances a few years. But the time that you experience doesn't change, and you will die at the same time you always died. It's just everything else outside the spaceship goes faster. Depending on the answer, I may be looking for a major change. You should create a space podcast. I've thought about that. Okay, so let's go to the next question. The force of gravity can pull on 5, 4, 3, 2, 1. And clearly you are all correct. The force of gravity can pull on everything. That'd be a beam of light, a massive object, neutrinos, and antimatter. And in fact, later in this course, we will show how the bending of light, because of the warping of space-time, has dramatic effects on our ability to detect distant objects. Okay. Gravity is described by general relativity as a bending of space, and particles, all particles, including light, move through warped space along curved space-time. So the observed slowing of a clock in the vicinity of a black hole is a prediction of extra credit for those who subscribe to Brand and the Space Podcast. Yes, certainly. By the way, for those of you that are on Twitter, I strongly suggest you follow Katie Mack, who's the other astrophysicist in our department who co-teaches this course, actually. And she's a very well-respected Twitter feeder. She also just wrote a book that's gotten reviewed in the New York Times called The End of Everything. It's a great book, by the way. Have you written a book? Yeah, I've written 2 books. I've written The Number by Colors, which is a book about human color vision. And I've written a book called The Data Handbook, which is about technical data formats. I wrote those books for my first and second startup companies, respectively. I started a scientific software company and a internet company. Oh, yeah, and I'm in the process of writing the 3rd book on the LSST telescope. So there's some confusion here. The observed slowing of a clock in the vicinity of a black hole is a prediction of. So certainly the manipulation of time is true in both special and general relativity. But slowing of the clock in the vicinity of a black hole is because the black hole has a very strong gravitational field. And gravity is the purview of general relativity. Okay? And we'll be talking about black holes later in this course. I would low-key listen to your audiobook to help me get to sleep. Not quite what I was looking for. If the Earth was replaced by one solar mass black hole, I love this question. I'm a hidden gem of NC State. Thank you so much. That's so kind of you. Should I make note of that and put that on your grade? No. We would all die is the answer. Actually, Matthew, that is exactly correct. We would all die. But I don't see that as one of the answers here. Life would be unchanged. Yeah, I don't think so. Okay, 5, 4, 3, 2, 1. Okay, so this would be a very, 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 very bad day. In fact, it would be the last day. But most of you got the wrong answer. And the reason why is that space-time don't care if you're a dog. If you have a 200-pound or a 300-pound dog and a 300-pound knee, we both warp space-time in exactly the same way, okay? And so if you have a 1 solar mass star and a 1 solar mass black hole, both of them warp space-time in exactly the same way. And so the correct answer is Earth's orbit would not change. Nothing would happen to our orbit. Now, we would all die, okay? But that's just a minor issue here, okay? So again, space-time only cares about mass. It doesn't care about the composition of that mass, Why don't we get eaten by the black hole? We don't get eaten by the black hole. So the only thing that black holes eat are things that get too close to it. And we would be just as far away from the black hole as we are from the sun. Nothing would change. Space-time would be warped in exactly the same way. It's only things that are headed towards the black hole that get ripped apart. If we did get eaten by the black hole, how long would it take? I have an entire lecture on that. And no, Mercury would not be eaten. How close is too close? We have an entire lecture on black holes where we will cover that exact question. Got one more question, then we'll open it up for, oh, I guess that is the last question. Okay. So I'm opening it up for any QA. And you're welcome to turn on your mic at this point. Is the only unique thing about black holes that they're usually so much more massive than other objects that have those weird effects? No. So the thing that's unique about black holes is that they're incredibly dense. And so if you notice the analogy of the fabric of space-time, he threw on a big, heavy mass. Now imagine if he had that big, heavy mass, but all that mass of that 10-pound weight was the size of something the size of a BB. Okay, so it'd be denser than anything that we know of. It would warp that fabric much more than an extended mass, and that's a black hole. You take something that's as massive as the sun and you compress it to something the size of Chapel Hill. And because it's so tiny, it warps space-time that much more. And so if you're very far away from it, it doesn't matter. But if you're close to it, that warping of space-time means that acceleration that you feel and that warping of time that you feel is extreme. And you saw that in the movie Interstellar. Is it possible for black holes to stop existing? Can they die? Oh, gosh. Yes, they can die. We don't talk about that in this course. It's called a Hawking radiation. And so black holes do evaporate, but that's beyond the scope of this course. Okay, there's a bunch of questions. Let me scroll back and get to them. So throw corona into the black hole. I'm not sure what that means, Alex. Sorry. How good would it feel to be eaten by a black hole? We actually talk about that in the lecture on black holes. It's called spaghettification. How many questions in the exam? I think right now it's about 67. Will we discuss string theory? Unfortunately, no. Sorry. The universe is so big and there's so many things we could talk about, and string theory is not one of them. Another reason we don't talk about string theory is we're not sure it's true. Is one solar mass in reference to the black hole? Yes, that's correct. Can we watch 2001 as a class? Oh, I wish. I would strongly recommend you watch it on your own, though. It is a great movie. So 2001 and Interstellar are the two greatest science fiction movies ever. Can we take you out to dinner after Corona has gone away? Oh, yeah. Boy, that would be wonderful. Thank you. Theoretically, would a black hole sink in water? Absolutely. It's the densest thing that we know. If you had a chance, would you jump into a black hole? No. And the reason why is that, Vegas, what happens in Vegas stays in Vegas. What happens in a black hole stays in a black hole. You go into a black hole, you ain't ever coming out. Okay. And again, we'll talk about that when we have the lecture on black holes. Let's watch 2001 at a celebratory dinner. Yeah, let's set up a screen on the outside and we'll all watch it. That would be wonderful. Is it possible black holes to stop existing? Can they die? Well, yes, they can die. It's only small black holes. Do we know what actually happens in a black hole? So not only do we not know what happens inside black holes, we can never know what happens inside black holes because no information can ever escape from a black hole. And the reason why is, as we'll get into, you remember we talked about the escape velocity in the previous lecture. A black hole is defined by where the escape velocity exceeds the speed of light. And since nothing can travel faster than the speed of light, no information can ever come out of a black hole. So we can never know what happens inside a black hole. So how do you reconcile classical quantum mechanics with general relativity? So Einstein spent most of his life trying to figure that out. And, he passed away in 1955. Since 1955, thousands of physicists have tried to reconcile quantum mechanics with general relativity, and nobody has yet succeeded. So that is, if someone could do that, that would be, well, they would just print out Nobel Prizes till the cows came home. So was there extension? Yes, I did extend the homework. So for those of you that are asking, I extended the homework for this chapter to today. But that would have expired by 10 a.m. today, sorry. Could you explain what exactly curved space-time is? Unfortunately, I tried to do the best with my explanation and having 3 or 4 videos trying to explain it. I could throw the equations on there, but that's not going to really help. I think the best way to think of curved spacetime is through that analogy of a 2-dimensional warp sheet. And that works, except you have to realize that not only are 2 dimensions warped, but there's a 3rd dimension that's warped, and there's also time that's warped. Spaghettification. You will wait until we talk about the black holes, where we talk about spaghettification. It's a fun subject. If the universe is constantly expanding at an accelerated rate, is there a time when things will accelerate faster than light? Yes. And in fact, that's happening right now. So Grayson says, is the universe expanding faster than the speed of light? So we have this concept of observable universe, the part of the universe that we can actually observe. And since the farther away things are from us, the faster they expand, at some point, that expansion rate is going to be faster than the speed of light. And what that means is we cannot observe anything past that boundary. And this does not violate the tenet, because the tenet is that no information can travel faster than the speed of light. And since there's no information that can ever come from beyond that line, then it doesn't violate that, that concept. What is your favorite topic in the course? I'd have to say the last couple of lectures, when we talk about cosmology and we talk about life in the universe, I'm very interested in. Although my research, when I was active in research, was neutron stars. What would we experience as a human being swallowed by a black hole? So here's the thing. You remember we talked about tides, where there's a different gravitational force on one side of the Earth compared to the other side of the Earth? Well, so tides is the difference in that warping of space-time between one side of the planet and the other side of the planet. And the thing is, the warping of space-time is so extreme around a black hole that your feet would feel a different gravitational force than your head. And that's a bad thing. You would be stretched out. That's not good. Are black holes wormholes? So the equations for black holes and wormholes are very similar. The problem is we know black holes exist because we've observed them. We've even taken a picture of a black hole. Wormholes are a mathematical possibility, but we don't think they're a physical possibility, because for wormholes to exist, we would have to have something known as negative energy, which most people think do not exist. But general relativity allows wormholes. I want to jump into a black hole. Matthew, knock yourself out. We'll never see you again. We should have a weekly movie club and watch the different sci-fi greats. Actually, that's not a bad idea. Does the Hawking radiation that you talked about contain information? Could you scan, collect to piece together information about events near a black hole? So Sam, that is a very, very active part of research, and there's an incredible amount of debate about that very topic right now, because some people are very upset with the concept that when you throw things into a black hole, you lose information. And other people say, well, you don't lose information. It's encoded in the Hawking radiation that comes from that. Unfortunately, that's beyond the scope of this course, but it's a fascinating subject. How do I turn my camera on? You clip on the video icon in the lower left of the screen, and you could do it there. Let's see, is there anything preventing wormholes from existing? No, other than the existence of negative energy, which we don't think exists. Have you seen Interstellar? I've seen Interstellar a couple of times, and at a film festival I sponsor, I was on the panel with Abercrombie, a guy who invented the concept of the Abercrombie drive, when we talked about the movie Interstellar. And this is at the Roger Ebert Film Festival I co-sponsor. What is a gravitational wave? We have an entire lecture on that. It's amazing. Are there any resources that you would recommend for those interested in learning about black holes? Oh, that's a good question. So Katie Mack's book, which is a great book, is about the cosmology, the end of the universe. Um, Let me think about that. You know, I think Neil deGrasse Tyson's Astrophysics for the Impatient is not a bad book, and I think it does talk quite a bit about black holes. How does the orbital speed of an asteroid and circular solar orbit with a radius of 4 AU compared to a circular solar? Can you explain? So Joseph, send me an email and I'll go over that. Really, it's p squared equals a cubed. So, so for a circular solar orbit with a radius of 1 AU, the time for that orbit would be 1 year. So p squared equals a cubed. If you measure p in terms of years and a in terms of AU, then 1 squared equals 1 cubed has to be true. So with the orbital radius of 4 AU, so 4 cubed, if you take the square root of 4 cubed, that would give you the period. So p squared equals a cubed. This class low-key makes me want to jump into a black hole. The only thing getting me through is this man's voice. Well, thank you. How do you see black holes? Do you need an X-ray telescope? We have a lecture on that. This was probably the most amazing scientific breakthrough of last year, where we actually took a picture of black holes using radio telescopes that surrounded the entire Earth. And we'll talk about that. We've got a bunch of topics about that. It's just an amazing thing. Have you read Physics of the Impossible? No, I've not read that book, but I've read a lot of other things that I'm sorry, I cannot pronounce his last name, Kaku has written. I mean, he's a bit out there, but I love his stuff. He's a legitimate physicist, but he's great. Other questions? So thank you for the questions. Thank you for the kind thoughts. Remember, the exam opens at Tuesday at 8 a.m. It closes Tuesday at 11:59 p.m. You've got 75 minutes. Any questions between now and then, send me an email. And
wait. So the study guide is like on Moodle, right? Or is it?
Absolutely not. The only thing on Moodle is the exam itself. Everything.
Oh wait, no. I want to talk about it. It's on WebAssign, right?
Everything you need is under Resources WebAssign.
Yeah. Okay.
And so that would be the exam guide. That would be the syllabus. That would be the formula file. That would be the PowerPoints from the publisher and my PowerPoints. Okay. If you want, you could totally give us the exam questions and answers. Yeah, I do. Yeah. Then it wouldn't be called an exam now, would it? Any other questions before we break? Thank you so much, and good luck.
Bye, I love you.
Thank you so much. I appreciate that. Thank you so much. I will actually
love you, Bran.
Thank you. I'll see you guys. Well, I guess I won't see you during the exam. Good luck on the exam. Shoot me any questions, and I'll see you all next Thursday. Good luck.
Thank you.
Thank you.